The 8 queens problem is to place 8 queens on an 8x8 chessboard so that no two queens threaten each other. This solution requires that no two queens share the same row, the same column, or the same diagonal. You've got one feasible solution that satisfies all the constraints on the left, and you've got a solution on the right that do not satisfy some of the constraints. For instance, you can see that in blue, there are two queens that are attacking each other on the same column, and in red, it's represented two queens that are attacking each other on the same diagonal. So this is not a solution. So to solve that problem, we need to think a little bit about the modeling of that problem and to decide what we need to decide to find a solution. One possible encoding is to use a Boolean matrix. In this Boolean matrix, you will have a value true that corresponds to placing a queen in that specific cell, and a value false means that you do not place the queen. Okay, the queen is not present in that cell. So if you want to encode the solution on the left, you encode it with the Boolean matrix that is represented on the right. The drawback of that approach is that you really need to check the three types of constraints: the same row, not two queens on the same row, same column, or same diagonal. An alternative modeling approach is to use an array of decisions, of integer decisions, that will tell you for every queen at that specific column in which row you will place that queen. So for instance, the queen at column number 0, you will, for instance, place it in the row number 2, and in that case, you put a 2 in that specific entry in the array at this location. If you want to place the next queen at row number 4, then you put a 4 in that specific entry, and so on and so forth. And so this is the encoding that corresponds to the initial solution that I have represented before. And as you can see, we've got an array of size L. The main advantage of that approach as a modeling approach is that you don't even need to check that no two queens are playing on the same column, because that's not even possible. Okay, since you have to assign one specific integer value for every row, because of that, it's impossible that you place two values inside a specific entry in the array. So you don't need to check the column constraint. You need to verify the same row and the same diagonal. So that's the main advantage. And so if you want to discover all the solutions to a constraint satisfaction problem, such as the NQueens problem, you want to think a little bit generic. One very generic approach is to generate all the possible assignments to the decision variables, and then we will filter the solution that do not satisfy some of the constraints of your constraint satisfaction problem. So let's try to apply this approach to the 8 queens problem. First thing that we need to decide is which encoding we will use in our implementation. Another consideration to take into account for the generate and filter approach is the number of candidate solutions that you might generate. For the Boolean encoding, you've got 2 to the power of 64, because there are 64 cells, a Boolean value for each of them, so that's 2 to the 64 possible assignment to this Boolean matrix. For this integer encoding with the one-dimensional array, you've got 8 to the power of 8, because you have 8 decisions, and every decision has 8 different values that correspond to each positions on a row. And so if you transform that into a power of 2, that's 2 to the power of 64, and this is much less than the number of combinations that you might generate for the Boolean encoding. And the reason that it's much less is simply because you are sure here that you will never violate the column constraint. But here it might be the case that you generate a solution that violates the column constraint. And that's the reason why we eliminate a lot of infeasible solutions just by using this encoding. So that's the encoding that we will choose for our problem. So if you want to generate all the solutions, a classical way to do that, to implement an algorithm, is to use depth-first search. In depth-first search, it's a very standard algorithm that is used to explore graph data structures, but it's also used to generate every possible combinations to a combinatorial problem. And so the encoding that we have chosen is the array representation, and we will use a specific pointer that we call index that correspond to the next queen that we need to decide. So let's assume that we have already placed this one in 1, 3, let's say, and this one is in 5. What is the next value that we need to decide is id x, and we will recursively use depth first search here. Okay, and that's the next entry that we need to decide is idx, and we will iterate over every possible combinations from 0 to n-1. And so what we are doing here is that we are exploring a tree. Okay, and that's the number of possibilities of branches that you create in this tree. Okay, and so on and so forth. And so this is really a tree that you are exploring here. Okay, and what you've got at the leaf nodes are all the candidate solutions. You reach a leaf node when your index is equal to n, which means that you have already decided position for every row for all the 8 queens. Okay, and what you need to do there is verify if all the constraints are satisfied or not. And this is what we will do here. Let's make it generic and let's call that constraint satisfied, like if it was a predicate. And so we return a Boolean here that is true if all the constraints of your problem are satisfied. How do we verify that all the 8 queens problem constraints are satisfied? Simply by checking for every pair. So we will check for every pair ij with I less than j if if the 2 queens I and j are not attacking each other. So they will be attacking each other clearly if they are placed on the same row, but also if they are placed on the same diagonal. And so in that case, you've got two possibilities. You've got this diagonal and this diagonal. Okay. And so what you will do is that you will verify that this is not a triangle there. So if the difference between the indices j and I is different from the absolute difference of the value that you have decided for the row, then, okay, so if this distance is not the same as this distance, then you are fine. You know that the 2 queens are not attacking each other on the same diagonal. Okay, and we treat both cases using the absolute value here. So this is quite a generic approach because we have implemented the verification of all the constraints in one method that is constraint satisfied. Okay. How can we collect all the solutions? To do that, there are two possibilities. Either you hard-code that inside your exploration algorithm, or you implement it in a clean way using the Hollywood principle that is also called don't call us, we'll call you. And so the way to implement this principle is in the clean way is to use lambda functions or closures. Lambda functions is usually the name that we use, for instance, in Python languages, and closures is more the name that we use for Java. So the way we will do that is that we will augment the signature of the depth first search with here the closure, the lambda function, and this function will be a consumer. The consumer is an interface that is available in Java. Okay, it's available there in Java util function consumer. Okay, and this function has just one single method that is accept. It's a generic type, so it's parameterized by the type t, and in our case t will be an array of integers. And so whenever a solution is found, your lambda function will add the solution that it has discovered, represented as the array of integer, and it will add it to the array list that will be eventually contain all the solution that has been found during the exploration of the search tree. Okay, so we augment the signature of the DFS with this lambda function. And again, we add this parameter also to the private depth first search that also contain the index, next index that you need to decide. In case all the constraints are satisfied, you just clone the array of the decision that you have taken so far, and you pass them to the function accept, that is the function corresponding to the lambda function. Okay, and the rest is left unchanged. So to wrap up, we have seen that we can use very generic generate and filter approach for solving the 8 queens problem. And we can also collect all the solution in a clean way using the Hollywood principle by augmenting the signature with a lambda function or a closure, and you can use functional interfaces of Java to do that.